This is the second part of the video in which I'm going over test number 2 on electrostatics and current. So we're up to number 11, and in number 11 we have a stretch of wire and a potential difference of 75 volts was placed from A to B. So there's 75 volts across here. We have two resistors in the middle, and these are in series, and that's the key thing to realize about this. It's not parallel, it's series. Okay, so the question was to just fill out the entire chart, everything that we can say about the circuit, the power, the potential difference, the current, and the resistance for the whole thing and for each individual resistor. Okay, we can fill in the givens. There they are. Okay, now next thing we can fill out is the overall resistance. Because these resistors are in series, we simply add. So that'll be 20.5 ohms total. Next, we can use delta V equals IR, Ohm's law, right there. Anytime we have two of those three in a row, we can get the third one. So I will be delta V divided by R. So we can divide, and we'll get 3.66 amps. Where do we go from here? Well, next thing we need to realize is that when the wire is in series, it's the same current throughout. It's the same amount of charge per second passing from A through to B. So, only if this branches out in parallel would the current split up. That doesn't happen here. So we know we can put in 3.66 amps here and here as well. Once we have those, we can use delta V equals IR, and we can multiply to get the delta V across each resistor. So that would be 29.3 volts across R1 and 45.7 volts across R2. All right, so we're almost done. Next part is to get the power, and once you have the rest, it's easy because power is voltage times current. So power equals delta V times I. So I just multiply these two to get this column, and that will be 274 watts overall. 274 watts delivered to the whole wire. For this one, it's 107 watts. And then for the last one, I can either multiply, or of course I know that these two powers have to add up to the overall power. Either way, I get 167 watts. Okay. All right, so that completes the chart for that circuit. All right, number 12. Number 12 has a proton moving at a given speed in the horizontal direction. It then enters a uniform vertical electric field with a given magnitude. Okay, so I want to draw the picture. So we have an electric field. Let's make it going up. We're told it's vertical. And here's a proton with its speed going this way. It's going to enter the electric field. Now, overall, what I want you to realize in this problem, right, is that this thing is going to, of course, move at a straight line. There's no other force, so it's going to have that velocity, constant velocity. Once it enters the field, though, that will exert a force, of course. This is a proton, so this is positively charged, and so it's going to feel a force in the direction of the electric field. So that's going to push it that way, right? So over time, it's going to have been displaced some vertical amount by the time it gets to the end of the electric field, or 5 centimeters horizontally is what we're going to be asked about. Okay, so this is two-dimensional motion, and what you need to remember then is that the horizontal and the vertical motions are independent of each other. The only connecting quantity between them is time. Time is the one bridge between the horizontal motion and the vertical motion. This is just sort of traditional projectile motion that we're talking about from first semester. So in question A, we're asked how long does it take for the proton to move 5 centimeters horizontally. This is starting when it enters the field. So 5 centimeters horizontally. Well, the thing is, here's its horizontal speed, and there's no force that's changing that horizontal speed. Horizontally speaking, we have constant velocity. Okay, so there's no acceleration, there's no force, nothing like that. It's really simple. It's just we're going this fast for 5 centimeters. How long does that take? Okay, so we just figure out time is going to be distance divided by speed. That's all. Again, no acceleration in the horizontal component of the motion. So we have 0.500 meters over 2.5 times 10 to the 5th meters per second. It's 2.00 times 10 to the negative 7th seconds. Okay, so now question B, how far does it move vertically in that time? So here's where we're looking for this distance. How far does it go in that time? How far vertically does it get deflected? So now, in the vertical direction, this is going to be constant acceleration motion, because we have a constant uniform electric field that's going to exert a constant force on our proton upward, and that's going to, through F equals ma, going to result in a constant acceleration. So let's work that out. So the force is Q times the electric field. So that'll be 1.60 times 10 to the minus 19 coulombs times the strength of the magnetic field, the electric field, 7,650 newtons per coulomb. So that's going to be a force of 3.52 times 10 to the minus 15 newtons. Okay. Then we use F equals ma. If that's the force on this proton, then we can get the acceleration by dividing force by mass. Mass of a proton, 1.67 times 10 to the minus 27 kilograms, giving us 2.11 times 10 to the 12th meters per second squared. All right, so now I have my acceleration, and that's constant acceleration. The whole time it's traveling through the electric field vertically. And so I'm going to go to my constant acceleration motion equations and pick the one that is going to give me my answer. So what do I have and what am I looking for? Well, I'm looking for how far it traveled. So I'm looking for a final distance, a final position. I'll use y just because we're doing vertical. Of course, the equations on our formula sheet use x, which is normal for horizontal motion, but that would just look weird to me, so I'll just change it to y if that's okay. So we're looking for the final position. Remember, we're always free to choose the initial position. We can make it 0, which we will. We have the acceleration. Already got that. We have the time from the previous problem. How about velocity? Well, we have the initial vertical velocity. Now remember, this is all vertical going on here, so maybe Vyi. Vertically, we started with 0 velocity. All the velocity we had was horizontal. The 2.50 times 10 to the 5th meters per second was all horizontal. We had no vertical velocity initially. Now we don't know the final vertical velocity, so we weren't given that. So let's not use an equation that involves that. Okay. So I think the equation to use is number 2 on our list of the 4 equations. So again, switching from x's to y's, we have yf equals yi plus vit plus 1/2 at squared. And we have everything. both this and this are 0. So really, YF is simply 1/2 AT squared. And we plug in the A and the T, and we get, whoops, timeout. I just caught a little mistake. Sorry about that. I typed in the wrong number back on the force here. My apologies. This force comes out to be, this should have been 1.22 times 10 to the minus 15. I just typo into my calculator. And that changes the acceleration to 7.33 times 10 to the 11th. Sorry about that. Yeah, this is 1.22 times 10 to the minus 15. So yeah, that changes that, which changes that, which now I will put this in, and we get 0.0147 meters, or 1.47 centimeters. So yeah, that's the correct answer. As it moves 5 centimeters horizontally, it will have moved 1.47 centimeters vertically in that time. Okay. Number 13. What is the speed of an electron that is accelerated from rest through a potential difference of 75 volts? So I think the easiest way to do this is using energy. We're already starting with volts, which is potential, so that's already setting us on the track of using the energy approach. And what we would do is we would turn that into potential energy using delta U equals Q delta V. It's an electron, so it's got a charge of negative 1.60 times 10 to the minus 19 coulombs. It's going across 75 volts. That ends up being negative 1.20 times 10 to the negative 17 joules. So the potential energy will have gone down by that many joules, which, since we're not told about any other force or anything else going on, that must mean that that energy went into kinetic energy. So kinetic energy went up by 1.20 times 10 to the negative 17 joules. And since it was starting at rest, it had 0 initial kinetic energy. So that must mean the final kinetic energy is, again, positive 1.20 times 10 to the negative 17 joules. Okay. And of course that equals 1/2 mv squared, final velocity squared. So you solve for the final velocity, the final speed, because that's what we're being asked for. Vf equals square root of 2 kf over m, then plug in that k, and you will get 5.13 times 10 to the 6th meters per second. And that's your final answer. Number 14, find the equivalent resistance between points A and B in the given figure. So we have 3 resistors. These two are parallel to each other, and then that whole configuration is in series with this one. So we do this in steps. These two together are in parallel, so we know we can combine them using the reciprocal rule. One over the overall resistance of those two guys is 1 over 65 ohms plus 1 over 85 ohms. When you add them together, and remember to then do the reciprocal to get back to R again, we'll get 37 ohms. So that these two, we can basically redraw this and think of it as a 63 ohm resistor and then a 37 ohm resistor. Just that 37 ohm resistor is equivalent to that situation right there. Okay. And now these two are in series, one after the other, and we know we just add them then. So this is the actual overall resistance for the whole thing, and we see that we get 100 ohms. So the equivalent resistance for the overall circuit, the overall stretch of wire, is 100 ohms. Number 15, a toaster is rated at 550 watts when connected to a 120 volt source. So the first question is how much current goes through the toaster. This is a pretty straightforward problem, I think. We just use our basic equations that connect these quantities. We have a power and we have a voltage, a potential difference, and we're asked for current. So this is the equation that will solve this situation. So 550 watts divided by 120 volts gives us 4.58 amps. Okay. B then is, what is the resistance of the toaster? So for that we can use Ohm's law. Delta V equals IR, telling us that R is potential difference divided by the current. So we do the 120 volts divided by the answer we just got, and we get a 26.2 ohms of resistance for the toaster. Okay. Number 16, we have a sphere made out of conducting metal. So that word conducting is important. We have a conductor here, and it has a given charge and it has a given radius. Okay, question A is, what is the electric field at a distance of 5 millimeters from the center of the sphere? Now I'm going to draw a picture. Here's the sphere. This thing has a radius of 12.5 millimeters. We're being asked about the electric field 5 millimeters out from the center. That point is inside the conductor. And here we don't have to do any math. There are no formulas. We just remember that inside a conductor, in electrostatic equilibrium, there is no electric field. The electric field is 0. Done. Question B is, what is the potential at the same point, a distance 5 millimeters from the center of the sphere? Okay, so for this, we're still inside the sphere. V is not 0 inside a conductor, but V is constant inside the conductor. So V, as we sort of approach, V is 0 at infinity, and it gets bigger, 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 and then once we get to the surface of the conductor, we're at the biggest number it's ever going to be, because as we drill inside and go inside, it stays the same. It's the same as it is right here. Okay, so again, whatever the potential is at the surface is also what it's going to be throughout. Conductors have one single potential, one V. All right, now the formula is the same as for a point charge, Ke times Q over R. But again, for R, we're going to put in the R for the full radius, because it stops changing after it gets to that point. It's constant once you get inside. So I'm putting capital R here, and that's where we're going to use the radius of 12.5 millimeters. So we will have 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. The given charge, positive 1.50 times 10 to the negative 6th coulombs. And we use the 12.5 millimeters, so 0.0125 meters. And this is going to give us 1.08 times 10 to the 6th volts. Okay, so again, the key here was noticing that it was a conductor, and we have special rules for conductors. E is always 0, V is always constant inside the conductor. The 5 millimeters was never used in any of the formulas. The 5 millimeters, all the 5 millimeters did for us in this problem is tell us that we were inside the conductor. That's all it did. We never actually used 5, because it doesn't matter if we're 5 or 8 or 1 or 10, as long as we're inside the conductor. Okay, number 17. 1¼ volt potential difference is maintained across a 2.5 meter length of tungsten wire that has a given cross-sectional area, and we are then given the resistivity of tungsten, and we want to know what the current in the wire is. All right, so the idea here is we're given a potential difference, and we're asked for current, so we're given a delta V, we're asked for I, and we should be thinking about Ohm's law at this point. Delta V equals IR, because we have we want I, we have delta V. Now it's just a question of getting R. If we can get R, we're good. R is the resistance. Now they haven't told us the resistance, but they've given us everything we need for resistance. So the formula for the resistance of a wire on our formula sheets was the resistivity times the length divided by the area. And we have all three of these. Right? Here's the length, here's the area, here's the resistivity. So other than we have to change this to square meters instead of millimeters, we end up, you plug all that in and we get a resistance of 0.233 ohms. Okay. Then we can go back now to delta V equals IR, so I is delta V divided by R. We can put in the 1.25 volts and divide by this resistance, 0.233 ohms. And we're going to get 5.36 amps, I believe. So there we go. Last question on the test, number 18, was a series of 3 true and falses. A. The electrons in a circuit connected to a battery come primarily from the wire itself. This is true. The fallacy is that the electrons come from the battery. By and large, this is not true. The battery just creates the potential difference, which drives the electrons that are already in the wire. B. When current moves through a wire, the electrons move in the direction of the current at very high speeds. This is false. It's false because of the very high speeds. The electrons are bouncing around in lots of directions, but the overall drift speed in the direction of the current is actually a low speed. And it can take many minutes, even up to measured in hours, for one electron to move an appreciable distance, to move a meter or so, a couple meters down a wire. So it actually goes very slowly in the direction of the current. And C, if you double the current going through a wire, that means that twice as much charge passes through a given point per second. That is definitely true. Definition of current is its charge divided by time. It's how much charge passes a given point per second. So if you double the current, you double the amount of charge passing any given point every second. So this is literally the definition of current that we're citing here, and that would be true. Okay, that's the entire test.